So reactions involving gases. Chemical reactions sometimes use gases as reactants, sometimes generate gases as products, and if we're measuring those gases, the most convenient thing to do is to measure their volume and temperature and pressure, and that way we can find the moles, because measuring the mass of a gas is a pain. So we use rearrangements of the ideal gas law to do these calculations. If it's happening at STP, things are much simpler. We can use the molar volume of a gas. 1 mole equals 22.4 liters. So that's really nice. You may be dealing with partial pressures in these problems, and so you have to watch out for that. So this is an illustration from the book showing the regular stoichiometry path. Grams to moles to moles to grams. And that's the basis of everything, and then we just switch up the ends. Mole to mole, moles in the middle, always. Always moles in the middle. So here, if we have pressure, volume, temperature of a gas, we can use the ideal gas law to convert that to moles of the gas. Moles in the middle, the mole ratio from the balanced chemical equation gets us moles of product, and then we can have information about pressure, volume, temperature of the product gas. Or we could still have grams at one end or the other. Or you could throw something like solution stoichiometry in there on one end, right? All kinds of fun possibilities. Okay, let's do a couple of relatively simple problems. In the following reaction, 4.58 liters of oxygen was formed at the pressure equals 745 millimeters of mercury and temperature equals 308 Kelvin. How many grams of Ag2O decomposed? So this is a chemical reaction. So we can't just take these volume, pressure, temperature and just go straight to calculating moles of something, because we need to know moles of what. So we're going to use the equation to organize our information. So the volume is the volume of oxygen, 4.58 liters. And they tell us what the pressure is, 745 millimeters of mercury. And the temperature is 308 Kelvin. So there's our volume, our pressure, and our temperature. And then what are they asking us to find? Grams of Ag2O. So normally we do grams to moles to moles to grams. And here we are looking for grams at the end, so that's going to stay the same. But here, that messed up G, we've got volume, temperature, and pressure of a gas. And we can go to moles directly using the ideal gas law. So the first thing I'm going to do is I'm going to use the ideal gas law to calculate the moles of oxygen. And then I'm going to continue on this path. So N equals PV over RT. Are you getting a little tired of converting millimeters of mercury and torr to atmospheres? It's always the same, isn't it? It's always divide by 60. So here's a shortcut. If this makes sense to you, go right ahead and use it. So here I'm going to write 745 divided by 760. The unit on that then would be atmospheres. So kind of simplifying it. It also saves you writing down more numbers. Volume was given in liters. That's a blessing. And then we've got our 0.08206 liter atmospheres per mole Kelvin. And the temperature was also given in Kelvin, so that was very kind of them. So I'm going to do 745 divided by 760 times 4.58 divided by 0.08206 divided by 308 equals So moles of oxygen equals 0.17763. That's moles of oxygen. I am now at this second point here. Now I can just use dimensional analysis. I'm going moles of oxygen to moles of Ag2O to grams of Ag2O. So I have moles of oxygen down here, and those are going to cancel out. And then here, I'm going to have grams of Ag2O in the numerator and moles of that in the denominator. Mole ratio comes from the balanced chemical equation. It takes 2 moles of Ag2O to make 1 mole of oxygen. So this is 2 to 1. And then I need the molar mass of Ag2O. So 2 times 107.9 plus 16. 2 times 107.9 plus 16. 231.8. Grams per mole. So 231.8 grams of silver oxide per mole. $82.351 grams, rounding to 82.4 grams of Ag2O. Any questions? Again, it's taking pieces we've looked at separately and sticking them together. You're doing a jigsaw puzzle or something. You figure out which piece and how do I put them together. How do you get good at this? You practice. A good place to start practicing is watch the video on YouTube, pull up this, stop it where it just shows the problem, try to do it yourself. Because you've seen it once, and so that should be easier than just doing a brand new problem. Try to do it yourself, and then you've got the video to help you through it. I'm doing the for practice problems. There's also practice problems in your textbook. Those are worked out in the book. So you can also just cover up the work that they show, try to do that problem by yourself, and then look at the work if you're getting stuck. One more, and we'll call it a day. How many liters of oxygen at STP are required to form 10.5 grams of water? Well, we've got one number here, 10.5 grams of water. So 10.5 grams of that. And what are they asking us for? Liters of oxygen. So here, question mark, liters, but then those beautiful letters, STP. That means things are going to be simpler. At STP. At STP means we can use 22.4 liters per mole. If you forget what that number is, but you remember that standard temperature is 273 Kelvin and standard pressure is 1 atmosphere, you can use the ideal gas law to calculate that. But we don't actually have to do that. So we're going to go, our path will be grams of water to moles of water to moles of oxygen to liters of oxygen. And this moles to liter, we can use the molar volume, 22.4 liters per mole at STP, and that is good for any gas. 10.5 grams of water. We're going to convert to moles. going to convert to moles of O2. And then convert to liters of O2. So dimensional analysis and our path, we can write all that out. Get all the units in place, and then the units are telling us where to put our numbers. So converting from grams to moles, we need the molar mass of water. So you can calculate that, or I've got it stuck in my head, 18.016. Moles in the middle, this mole ratio. 1 mole of oxygen makes 2 moles of water. 1 mole of oxygen, 2 moles of water. And then this one at the end is easy because it's the molar volume of the gas, 22.4 liters per mole. .5275 liters. Rounding that gives us 6.53 liters of oxygen. Any questions? Then we'll save the rest of that for next week.